Hello, I'm Jungmin Shin. Today I'll present about my paper, Prediction of Light Extraction Efficiency using a Transfer Learning Model. This paper was published to Nanophotonics in 2025. So let's start with OLED. OLEDs are organic light emitting diodes that use organic materials to produce light. They have the advantage of being thin, flexible, stretchable, and backlight free. OLEDs are currently used in many display industries, including virtual reality and augmented reality devices. OLED device consists of several basic layers, as shown in slide. The emissive layer, which is EML, is sandwiched between the hole transfer layer and electron transfer layer. Outside this, hole injection layer and electron injection layer, anode and cathode are located. The entire structure is built on the substrate. Light extraction efficiency, which is defined as the ratio of outcoupling light intensity to the light intensity generated in the emissive layer, is key performance factor for OLEDs. It reflects how effectively the device emits light and is directly related with the reliability and lifetime of the device. However, due to the internal reflection, only a small amount of portion can extract from the device. Mm, Otherwise, the light are trapped in substrate mode, waveguide mode, or surface plasmon polariton modes, depending on its wave vector. Given that the refractive index of the organic layer is around 2, the outcoupled light portion in the typical planar OLED is less than 25%. This low efficiency drives researchers to optimize the device structure to improve LEE. Accurate LEE calculation is essential for this optimization process. The most common way to calculate optical properties, including LEE, is solving differential equations using methods like FDTD or FEM. These methods allow for the analysis of complex structures with high geometric freedom, such as corrugated surface or metastructures. However, these are computationally expensive and time-consuming. To speed up this process, the multi-layer planar model called CPS is often used. Although CPS is limited to the planar structure and offer less structure flexibility, it is around 10,000 times faster than FDTD, make it ideal for small-scale optimization. However, when optimizing structure with a large number of design parameters, even CPS may not be fast enough. To overcome this, machine learning-based LEE prediction method has emerged. But so thanks to this speed boosting of the machine learning, they enable large-scale optimization would be possible. Previous work has shown that machine learning can be used to predict the LE of planar layered structures. With 6 structure parameters, the prediction time can be reduced to just a few microseconds. This approach uses a fully connected deep neural network to predict the LE spectrum in visible range. Uh, by, by this machine learning, single prediction can be up to 10 to the 9 times faster than FTTD and 10 to the 6 times faster than CPS method. However, like most neural networks, this model needs to be retrained whenever the target structure changes, which limits its flexibility when applied to different design space. Uh, so let's take a look at the simple example. Suppose we have a planar structure and we use the thickness and each layer as an input parameter. In this case, we first need to generate the data set by simulating many different combinations of the layer thickness. And based on this data set, we train the neural network. Once trained, the network can predict the LE spectrum for any combination of layer thickness with microsecond level. However, generating the we need to focus that the generating the data training data set is the most time-consuming part of this process. Uh, Now let's say the structure changes as shown in this figure. In this case, an additional layer is added, so we need to generate the training set again from the scratch and train based on this new training set. And when we just change some several structure, this process has been repeated. It is clearly data inefficient. Uh, so to address this, we consider reuse the previous data set, even if its input dimension doesn't match the new structure. By doing so, we can significantly reduce the overall training time. Uh, we use the transfer learning to reusing the previous data and previous pre-trained network. So in transfer learning knowledge, whether it's just object recognition, game strategy, or some physical behavior, all of that information can be passed on by reusing and adapting the network layers. This is especially useful for our case, where data generation is the bottleneck of the entire training process. By leveraging the transfer learning, we can drastically reduce the amount of training data uh, while still maintaining high prediction accuracy. Uh, there are several previous studies have demonstrated the effectiveness of the transfer learning in nanophotonic design and other scientific problems where data is limited. Uh, so these examples shows that knowledge can be successfully transferred between the different physical system with to share the similar conditions. Inspired by these successes, we adapt a transfer learning strategy for OLED optical simulations. In our approach, we apply transfer learning to the OLED structure shown in this figure. We aim to modify the LE spectrum by adding new layer while keeping the electrical property unchanged. So we place the additional layer between the capping layer and the cathode. Next, we define our network structure architecture. First, we train a fully connected deep neural network to predict the LE spectrum for the base OLED structure without any added layer. We call this model BaseNet. For the modified structure with one additional layer, we build the second network by transferring layer from the BaseNet. We call this new model the transfer net. Because transfer net reuses physical knowledge embedded in the pre-trained layers, it requires far less new data set and significantly lower training cost. To ensure optimal performance of the transfer net, we fine-tuned key hyperparameters, specifically the number of frozen layer and training sample size used for BaseNet. So interestingly, while the number of frozen layer has a strong influence on the final performance, the number of training samples for BaseNet does not significantly impact transfer net accuracy, unless the number of training sample for transfer net is extremely small. Based on this observation, we fix the BaseNet training size to only 2,000 samples. The graph on the right summarizes two comparisons. First one is how the number of frozen layers affect the amount of trainable parameters when BaseNet is fixed at 2,000 samples. Second one is the rightmost one, is how show how the BaseNet is and transfernet sample size impact the model's trainability when the number of frozen layer is fixed to 6. The interesting point in this part is TransferNet consistently perform best when the number of frozen layer is set to 6, regardless of the training sample size. I guess the reason why the moderate number, like 6, of 6 layer, given the best result is too many layers will reduce the number of variables that can be learned, and too few layers will result in poor transfer of existing information. So far, we've considered adding only one additional layer between the capping layer and the cassette. Now we extend this by adding 2 or even 3 layers in that region. As more layers are added, the difference between LE spectrum between the original and modified structure become more pronounced. Uh, with small training sample size, such as 500 sample size, TransferNet consistently outperformed DirectNet in both accuracy and stability. Uh, so when we further apply this transfer learning approach to OLED structure with, like I said, 2 and 3 additional layers, even that case, there are more complex case demonstrate superior performance and significant better tolerance to limited data. So it shows the transfer learning shows like high data efficiency and high tolerance. So this is one part of our paper, and next we will deal with the error prediction network. In real-world application, several types of errors can arise. First is simulation error that occur when using approximate methods such as like perturbation theory, which rely on certain assumption. Second one is fabrication error that happen during the manufacturing process, often due to limitation of like control or precision. Finally, measurement error can also occur during the experimental process, especially the experimental evaluation stage. Both the fabrication and measurement errors are unavoidable when moving from theory to actual device. To address this, we introduce an additional neural network designed to predict the impact of such errors on optical performance. This error prediction network is trained on data set that include realistic variations in parameter like layer thickness and refractive index. By doing so, we can compensate the performance degradation due to fabrication or measurement inaccuracy. So far, we've used transfer learning to improve the performance, speed, and stability. In this section, we use the transfer learning for predicting systematic error. So this schematic shows the architecture of our error prediction network. And as I said, we focus on systematic error, which follow the uh, predictable pattern. Uh, it is different from the random error because we cannot predict. any of the structure cannot the random errors. So we only focus on the systematic errors. To train the network, we generate the synthetic experimental data by applying randomly selected error function to the input. This function simulated realistic deviation, mimicking the kind of error observed in experiments. So let's take a quick look at the error function. The randomly selected error function follows the specific rule. The error, defined as the difference between the target and actual value, is modeled as a quadratic function of an actual input parameter. The coefficients of this function are chosen to satisfy predefined inequalities. So which is we set the difference between the actual and target value to the error, which is represent to y, and it is the function of the x and ax squared plus bx plus c, and in that case, a and b and c is randomly selected between the minus 0.1 divided by 3 to 0.1 divided by 3. So we assume the error depends only on the actual input value and not on the target or other external factors. So at the bottom there is one of the example of the error functions. So there, if we have separate error function per each input parameter dimension. So if we have 6 dimension input parameter, we also have 6 different uh, error functions. So our final model called ExpertNet is designed to predict the LED spectrum under the realistic experimental condition. In the case shown here, the standard deviation of the added random error is 0.01, which is the random error is 0.01. And this means no model can achieve the prediction error lower than 0.01. But the ExpertNet achieved an RMSE with 0.0112, which is very close to the theoretical limit. So we can say that the model is well trained and highly accurate. However, ExpertNet only predict the LED spectrum. It does not directly reveal how much the physical structure has deviated due to the fabrication errors. Since the experiment net is built by the combining of the Ethernet and BaseNet, and among that Ethernet predict the structure errors. So when we can separate the extract the predicted error function for bring the Ethernet when we bring the Ethernet. So on the left, I guess on the right, we see the error function predict by the Ethernet for parameter H1, H2, H3, and H4, and N1, N2. What's interesting here is that although the LE prediction is highly accurate, the predicted error function for H2 is significantly less accurate, even for other case. This behavior is also observed in other network with different random error like 0.02 or others. So so we need to figure out why it happens. So we figure out the inaccuracy of in predicting H2, and it still remains even when we remove the random noise from the LE spectrum. So in that case, the the Ethernet without the random noise, it still shows 10 larger than 10% error to predict the H2, the error function of the H2, while the other parameters remain within acceptable error margin. To validate this observation, we conducted a sensitivity analysis. Each structure parameter was varied by 5%, and we measured the resulting change in LEE. The graph on the right shows this result. As we can see, the change in LEE is relatively small when H2 is perturbed, indicating that H2 has minimal influence on the optical response. This helps explain the poor prediction accuracy for H2 since it has small effect on LEE. The network received weak learning signal for this variable. Interestingly, this also reveals an inverse relationship. The less variable impact to the LEE, the more difficult it is to accurately predict its error. Finally, we analyzed how the network prediction performance is affected by the level of the output random error. First, it's important to note that RMSE of ExpertNet is fundamentally bounded by two limits: the intrinsic accuracy by the basenet and noise floor induced by the random error. What's notable is that just over 60 experimental examples, ExpertNet performed closely approach this theoretical limit. This highlights that training on accurate error prediction model doesn't require a large dataset, and that transfer learning greatly improves data efficiency. And in the graph on the right, we show the reduction in RMSE when using EtherNet compared to when it's not used. For a structural variable like H3 and H4, which have strong influence on LEE, the predicted standard deviation remained below 0.2, even when trained with only 60 samples. This means EtherNet is still able to function effectively under noise and allow us to reduce the effective error by more than 80% through post-processing. In summary, we developed a transfer learning based prediction framework that achieve up to 2 times higher data efficiency compared to conventional neural network. Moreover, with just a few dozen experimental samples, our model can reliably predict both LE spectra and structure fabrication errors. This approach provides a scalable, accurate, and data-efficient solution for the optical design of next-generation OLEDs and other nanophotonic devices. And thank you for listening. If you have any question, please send to email. Thanks.